Hi everyone, I'm Yassis and I'm excited to present our paper on intracranial aneurysm pose estimation with DeepLearning at MICCAI conference. Intracranial aneurysms are abnormal focal dilations of cerebral blood vessels, typically small structures ranging from 1 to 30 millimeters. Detecting and evaluating them rely on tough MRI data. However, navigating through different 2D cut planes for aneurysm localization and adapted visualization is a difficult and time-consuming manual task for radiologists. Our goal in this work is to create an automated system that assists radiologists in detecting and providing appropriate visualization of aneurysms based on their orientation. This visualization approach simplifies the analysis of aneurysm structures and their connections to parent vessels. In computer vision, this task is known as pose estimation, involving estimating an object location and orientation from an input image. To facilitate the creation of larger datasets, we adopted a simple and fast annotation approach. We approximate each aneurysm with a sphere defined by two critical points, one at the neck P1 and another at the dome P2. This annotation provides details about the aneurysm location as well as size and orientation indicated by the vector V from aneurysm center to the dome. After generating these aneurysm annotations, the next step is selecting training samples. We rely on small 96 by 96 by 96 voxel patches. These smaller patches allows us to extract multiple non-overlapping patches per patient, enhancing the creation of more extensive training sets and improving background modeling. Now the challenge is how to choose these patches within the overall patient volume. For negative samples, we select a total of 14 patches per patient, primarily centered on blood vessels. This strategy enhances the model ability to efficiently differentiate between healthy and pathological vessels. Considering the rarity of aneurysm in MRI data, positive patches are centered on aneurysms and duplicated 50 times. Furthermore, we apply random deformations to each positive patch to generate a diverse range of aneurysm shapes. Our approach is based on a 3D end-to-end anchor-free CNN adapted for both pose estimation and object detection tasks. For pose estimation, we identify aneurysm by regressing their center coordinate C and defining their orientation using the size and orientation vector V. For object detection task, since most aneurysms are ball-shaped objects, detect them using spheres defined by the center coordinate C and the radius equal to the magnitude of the orientation vector V. To handle scenarios with multiple aneurysms in a single input patch, our architecture employs a grid-based approach. The 96 by 96 by 96 input patch is divided into 12 by 12 by 12 grid cells. For each positive cell containing an aneurysm center, the architecture predicts a confidence score, the aneurysm center coordinate C, as well as the size and orientation vector V. To evaluate the effectiveness of our proposed method, we conducted a five-fold cross-validation study using two large datasets, including the CHUV public dataset. For pose estimation, given the absence of existing state-of-the-art baselines, we executed the experiments on the two datasets. Localization error is measured by the Euclidean distance to the corresponding ground truth center, while the orientation error is measured using cosine similarity between the orientation vectors. For instance, in the public dataset, our method demonstrated a median localization error of 0.48 mm and orientation errors of 12.27 degrees. For the object detection task, our evaluation is based on an intersection over union equal to 10%. We compared our method with two fully automated state-of-the-art detection and segmentation baselines, namely NN detection and NNUNet. Our method demonstrated very competitive performance, achieving an average precision of 76.60%, a sensitivity of 82.93%, associated with 0.44 false positive per case. Now, let's see some qualitative results. The reformatted cut plans were automatically generated by our method, which align and orientate around aneurysm orientation. In Figure 1, our method detects a very small aneurysm with a low localization and orientation errors. Figure 2 demonstrated the detection of a spherical shaped aneurysm, while Figure 3 showcases our method ability to handle more complex shaped aneurysm. Even though the large orientation error of 41.54 degrees is primarily attributed to the ground truth annotation uncertainty on such complex shape. In Figure 4, we illustrate our method's capacity to detect an unlabeled aneurysm. To conclude my presentation, I presented our proposed method showed promising results for both pose estimation and classical object detection tasks. Large orientation errors are primarily due to the annotation uncertainty, in particular for small and complex shapes aneurysms. Future work will be focused on developing a clinical definition of aneurysm orientation, as well as conducting a real clinical evaluation of our method. Feel free to explore our paper for more details and access to our code and annotations at the following link. Thank you.